Hi everyone. Today let's talk about session 3.3, relations. Today we will define relations. We will learn the difference between a relation and a function. We will discuss examples of relations, and we will learn some properties of relations and some special types of relations. A relation from one set to another is simply a set of ordered pairs, a way of relating elements of one set to elements of another set. It can be thought of as a table which shows how elements of the first set relate to which elements of the second set. And here is its formal definition. A binary relation R from a set X to a set Y is a subset of the Cartesian product of XY. If the ordered pair XY is in R, then we write XRY. If X equals Y, then we call R a binary relation on X. And then a function is just a special type of a binary relation. So we call that a function f is a relation with these properties. Okay, the domain of f is equals x. So we require all the elements in x. They get mapped to some elements in the set y. Okay, so second, for all x in the set x, there is exactly one y in y such that xy is in f. Well, actually the first property, we say that f is defined. Right? F is defined for all the x in the set x. F of x is get mapped to some element of y. And the second, each element of x, we only map to exactly one element of y. Okay? So then we can say f is well defined. However, a relation does not have these restrictions. Okay, so let's look at examples. Let R be a relation from X to Y, where X equals Tom, Jane, Susie, and Y equals Cat 1, Social Science 101, Discrete Math, and R has the rule Person X take course Y. And then we can have the relation like Tom take calculus 111, Tom takes social science 101, Jane take calculus 111, Jane takes social science 101, Jane takes discrete math, and Susie take calculus 111. Okay, so this is one relation. You can see one person can take 3 courses, right? So that's why we don't. This is different than function. Functions for x, for one input x, we only map to one output y. But here, you see the input x, Tom, can map to 3 different courses. In this case, 2 courses. But Jane can map to 3 courses. Okay, so this is relation. They are related. Relation is more general than function. Okay. Next example. Let x be 2, 3, 4, and y be 3, 4, 5, 6, 7. If we define the relation R from x to y by saying the ordered pair x, y in R if x divides y, or by saying x, R, y if x divides y. Okay, now let's see. What is that? So the relation equals... Okay, 2 divides which elements? Well, we know 2 divides 4, 2 divides 6, so we can put 2, 4, and 2, 6. Okay, that's the element 2. How about 3? 3 can divide 3, 3 can divide 6, so we have 3 first. And then we have 3, 6. And then 4 can only divide 4, right? So this is the relation R. And we can also draw a table to denote the relation. So let me draw a table here. So we have x and y here. X 2, 4, 2, 6, 3, 3, 3, 6, 4, 4. Okay, and this table also denotes the relation. Okay, let's continue. We can define a relation R on the X. X is 1, 2, 3, 4 by XRY if X less than equals Y. Okay, please remember a relation on X means the relation is a subset of X Cartesian product with X. This Cartesian product can be also written as X squared. It's like R2 is our Cartesian product with R, right? Okay, now let's see. Let's look at the first element, 1. Well, 1 is less than equal to all numbers in the set X. So that's why we have 1, 1, 1, 2, 1, 3, 1, 4. And then we have the element 2 is less than equal to 2, 3, 4, right? So 2, 3, and 2, 4. And then element 3 is less than equal to itself and 4. Finally, element 4 is only less than equal to itself. So this is the relation in this case. Okay? Next. 1 can represent a relation with ordered pairs or by using digraphs. A digraph is a directed graph represented with digraphs with using vertices and directed edges with possible loops. Okay, for example, we consider the relations AA, BC, CB, and DD. Okay, so here, let's say A is here, and then B is here, and C is here, D is here. So A, B, C, D. Okay, then let's look at the relation AA. Then we get a loop, okay? B, C, so from B to C, so we get a directed edge. CB, oh, so CB, we can go back. DD, we also get a loop at the D. Okay? So we usually use digraph to denote the relation on a set X. Okay, so to denote on the set X. Okay, so if we have X and Y, usually then people will draw this X and Y, and then they put arrows here and there. Okay, but when we have the relation on a set X, then we can use digraph to denote the relations. Let's continue. Okay, a relation on X is reflexive if XX is in R for all the X in X. Okay, example. Let R be a relation on the X A, B, C, D where R equals A, B, C, C, B, D, D. Is F reflexive? What would you need to be added to R to make it reflexive? What would the digraph of a reflexive relation look like? Okay, is this reflexive? Does it contain all the pair of the elements itself? Let's see. It contains AA. Okay, let's look at element A. It contains AA. Let's look at element B. Does it contain BB? No. So it's not reflexive because BB is not in R. Does it contain CC? No, so CC is also not in R. Okay, and it also contains DD. So how to make R reflexive? Okay, we need to make it reflexive, we need to add BB and CC to R. Okay, and what would the digraph of a reflexive relation look like? Well, if it's reflexive, think about it. If we have 4 points, if it's reflexive, then we require what? We require each point has a loop. Okay, so each or every vertex has a loop around it. Okay, so this is the properties of the digraph of a reflexive digraph. Okay, next, a relation R on X is symmetric if for all xy in X. If xy, the order pair xy is in R, then the order pair yx is in R. Example, let R be a relation on X, A, B, C, D, where R equals AA, BC, CB, AC, DD. Is R symmetric? What would a diagram of symmetric relation look like? How would we define symmetry using logic notation? Okay, is this symmetry? So symmetry means if xy is in R, then yx must be in R. Let's look at the R. So we have BC, well then CB must be in R, right? We have AC, so we need CA is also in R, but here we don't have the CA, so R is not symmetric, because it means CA, so CA is not in R. In order to make R to be symmetric, we just add the CA in it. Okay, what would a diagram of a symmetric relation look like? Well, symmetric relations, so if we have like A here and C here, right? So if we have AC, then we should have CA. So a symmetric digraph, whenever there is a directed edge from A to C, there is a directed edge from C to A. Okay, so whenever there is directed edges, from A to C, then there is a directed edge from C to A. Okay, so you see this kind of graph. Okay, how would we define symmetric using logic notation? Well, let me use a different color here. So that is for all x, for all y, if xy is in R, this implies yx is in R. So this is the logic notation. So far, so good, everybody? Okay, let's continue. A relation R on X is anti-symmetric if for all xy, if xy in R and yx in R, then x equals y. Okay, let's see example. Let R be a relation on the set X contains the elements A, B, C, D, where R equals AA, BC, CB, AC, BD. Is R anti-symmetric? So anti-symmetric is like the opposite of symmetric. So the graph won't allow you to see this. So at any two vertices, there could be only one edge connect them. There cannot be like two edge connecting them. Okay, so let me draw it here. So, which means if you have BC, then you cannot have CB in the relation, because otherwise you have to require B and C is the same. But in this case, B and C are different. So we can say R is not symmetric because BC and CB both in R, and B and C, they're different. Okay. What element of R would we remove to make R anti-symmetric? Okay, we can remove BC, or we can remove CB. Okay, just remove one of them. And because AC is there by itself, we don't have CA, so that the AC is fine to leave it there. What would a diagram of anti-symmetric relation look like? Okay, so in this case, we would say any pair. So from A to C, we only see like a one edge. So any pair of vertices, there is only one directed edge connecting them. Okay. Next, is it possible for a relation to be neither symmetric nor anti-symmetric? Yes, our example. Okay, so yes, our example R, so this R is neither symmetric nor anti-symmetric. Because there are some pair of vertices, you see the two directed edges, and there are for some other pair of vertices, you see only one directed edges. So symmetric require all the pair. So all the pair of vertices, you either have no edge or you have two edges, directed edges. Okay, and for the anti-symmetric, for any pair of vertices, you can either have zero edges or you can have only one directed edges between them. Okay, let's continue. A relation R on X is anti-symmetric if for all xy. If x is not equal to y, then xy is not in R, or yx is not in R. A relation R on X is anti-symmetric written formally. Okay, so let's see here. Okay, yes. So we can also write down this contrapositive. Okay, so this guy, the contrapositive statement is okay. So we get not Q implies not R. Okay, so not Q is XY in R, but because it's or, it will become and. Okay, and YX in R. So this is not Q, and this guy implies not P, which is X equals Y. Okay, so this is exactly here. So far, so good, everybody? Okay. So let's keep going. A relation on X is not anti-symmetric written formally. So we already have this guy. So, okay. So sorry, not anti-symmetric means not this guy. Okay, not this guy. What would the not do? So for all, the not become there exists X, there exists Y, and okay, not of this guy. Okay. Let me recall you. Do you remember? Let me use a different color here to remind you. Do you remember that P implies Q? Let me put here. P implies Q is equivalent to not P or Q. Do you remember that? Okay, if you don't, it's okay. Let's draw the logic table. PQ, true, false, false, true, false, true, false. Okay, P or Q is only false when P is true and Q is false, and then the rest are true. Okay, not P will be false, false, true, true. Okay, so false, false, true, true, and you use it to do or true, 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 false, true, false. Okay, the or is only false when both of them is false. If one of them is true, then it's true. So now you can see they are the same. So then we know P implies Q and the not P or Q are equivalent. Okay, so now we have this guy. This guy is P, okay? So this is P, this is Q, and so P implies Q is equivalent to, okay, let me put this sentence there. Okay, so P or P implies Q will is equivalent to not P. So not P is then not so okay, this guy, let me see, where do I put it better? Okay, so this guy is equivalent to not P or Q, but because you have a not there, so when you distribute the not P becomes P, and then the or become and not Q. Okay, that's why here you should put P and not Q. So P is XY in R and YX in R, and not Q. Not Q is not X equals Y, so which means X is not equal to Y. So that's why we get this last statement. So far so good, everybody. Okay, let's continue. A relation R on X is transitive if for all x, y, z in X. If x, y, and y, z in R, then we have x, z in R. Okay, let's draw a picture. What does that mean? So if we have x, y, z here, if x, y in R and y, z in R, that implies xc is also in R. So it looks like you have those triangle shape of graphs for every 3 vertices. Okay, let's continue. A relation R on X is a partial order if it is reflexive, anti-symmetric, and transitive. Oh, I forgot to give you a transitive example. Let me give you a transitive example. Okay, R is, let's say, 1, 2, and 2, 3. So if 1, 2, 2, 3 is in there, then we must have 1, 3. Okay, or we can also have 1, 4. So this is the example. Okay, so let's continue. So partial order if R is reflexive, anti-symmetric, and transitive. Oh, you might say, oh, what is that? What does that mean? Okay, I can give you an example. Okay, so example of partial order. Well, let x be the real numbers. Okay, for real numbers, you see we have 2 vertical lines to denote it. And let R be, okay, so let R be the relations that X, so let's denote, okay, X, Y in R if X less than equal to Y. Okay, so this is an example of a partial order. It is reflexive because for all elements, we know x is less than or equal to x, right? It's anti-symmetric. So if x less than or equal to y and y less than or equal to x, then we know that x must be y. Okay, and it's transitive if we have x less than or equal to y and y less than or equal to z, then we have x less than or equal to z. Okay, so this is an example of a partial order, and that's why some textbook use the notation. So we denote the partial order to be x. This symbol really looks like less than equal, isn't it? But it just the symbol is more curvy rather than compared to the less than equal symbol. Okay. All right. Let's continue. Let R be okay. Let R be a partial order on the set X if X, Y in X, and well, we have either X is XR, Y or YR X, then we say X and Y are comparable. Okay? So, and furthermore, if every pair of elements is comparable, then R is a total order. So far, so good. Okay, let R be a partial order on the set X if X, Y in X and X is not real. Okay, X, Y is not in R and Y, X is not in R, then we say X and Y are incomparable. Okay. Let's look at some example. Let X be the set 2, 3, 4, 5, 6, 7, X, R, Y if X divides Y. Is R a partial order or is R a total order? Okay, let's see. Let's figure out what is the relation. Let's look at the element 2. 2 divides what number? 2 divides 4. Let's count the smallest. 2 divides 2 itself. 2 divides 4. 2 divides 6. And then let's look at 3. 3 divides 3 and 3 divides 6. And then 4 divides 4. 5 divides 5. 6 divides 6. 7 divides 7. Okay, first of all, is R reflexive? Yeah, because it contains 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7. So it is reflexive. Is it anti-symmetric? Okay, is it anti-symmetric? Yes, it has for different pairs of vertices, you can see there's only one edges between them. So you see 2, 4, but you don't see 4, 2. You don't you don't go backwards, right? So you have 2, 6, but you won't see 6, 2. You have 3, 6, but you won't see 6, 3. So it is anti-symmetric. And is it transitive? Transitive. Okay, so here it is transitive because here you see even though we don't here are the we can only see like X, Y in R, but Y, Z, we don't quite see a different Y, Z in R, but it's okay. So we can look at, I mean, the only thing will work is like 2, 4 is in there, 4, 4 is in there, so 2, 4 is in there, but this is not quite because it's 2, 4 is the same element as 2, 4. So here we don't have a shape of this. Okay, so this is transitive. Okay, so if we have this shape, then we must have this guy. But here, a lot of pair is just like this shape. We don't have another vertex edge connect them. So that's fine. We will say it is transitive. So yes, R is a partial order. Okay, and then is R a total order? Okay, so is it true that all elements in the set we either have x divides y or y divides x? Not really. Why? So you can see here the vertex. So okay, let me see. The elements 2 and 4, they are comparable, right? Because 2, 4 is in R. However, the elements 2, 3, they're not, okay? They are not comparable because 2, 3 is not in R and 3, 2 is not in R. Okay, so 2 does not divide 3 and 3 does not divide 2. So that's why we say R is not a total order. Okay, so this is an example that we have a partial order but not a total order. Okay, however, the ordering of elements that we mentioned before is a total order. Okay? Yes, the ordering on the real number lines is a total order because pick any number, any two numbers in the real line, we know we can compare which one is smaller, right? Okay, let's continue. Let R be a relation from x to y. The inverse of R denotes R inverse is defined by yx such that xy is in R. Okay, so let's look at this example first. Let x equals 2, 3, 4 and let y equals 3, 4, 5, 6, 7. X, R, y. If x divides y, find R and R inverse. Okay, so R equals, let's look at the element 2. 2 can divide 4 and 2 can divide 6. Element 3, 3 can divide 3. 3 can divide 6. Element 4, 4 can divide 4. And that's it. Right? And what is R inverse? Well, it's simply just switch the x and y. So here we get 4, 2. Here we get 6, 2. Here we get 3, 3. Here we get 6, 3. Here we get 4, 4. And that's it. For every order pair, we just switch the x and y, and then we get the R inverse. So far, so good. That's inverse relation. Let's continue. Okay, composition of relation. Let R1 be the relation from x to y and R2 be the relation from y to z. Then the relation of R2 composite of R1 is the relation from x to z defined by R2 composite R1 is the set of order pair xy such that xy is in R1 and yz is in R2 for some y in y. Okay, so if we draw the picture, we have x, y, and z, right? And this is R1, this is R2, and then this guy is R2 composite with R1. Okay, so how to find composite relation? Let's look at this example. So we have we have R1 is 1, 2, 1, 6, 2, 4, 3, 4, 3, 6, 3, 8. Okay, so in this case, it's better to draw some table. Okay, let me draw some table. So we have X, Y, and Z. So 1 map to 2. 1 can also map to 6. 2 map to 4. 3 map to 4. 3 also map to 6. 3 also map to 8. Okay, so that is R1. How about R2? 2 map to U. So let's write down the elements is U, S, T, U. So 2 map to U, 4 map to S, 4 map to T, 6 map to T, 8 map to U. Okay, now let's go along different path. Okay, so R2 composite with R1. Okay. So let's look at the element 1. The element 1, let me use a different color, then you can see how I walk. So let's follow the order so we don't miss any path. First path, go straight and go straight. So we have 1U. So far so good, everybody? Okay, let's continue. The next path, we go to 6, and then there's only one path. So we go to T eventually. So that is 1T. Okay, and that's the 1. Let's go to 2. So 2 go to 4, 4 can go to S. So we have 2S. 2 go to 4, 4 can go to T. So that is 2 go to T. And then 3 can go to 4, 4 can go to S, right? So we have 3S. 3 can go to 4, 4 can go to T. So this is 3T. 3 can go to 6, 6 can go to T. This is still 3T. Okay, but even though it's different path, but the relation is still 3T. 3 can go to 8, 8 can go to U. So, that's 3U. Okay, now we have gone through all the paths, and this is the compositions. Okay, so for compositions, we just draw the table and then imagine what happened when you go to different paths, and then you figure out the start points and the terminal points, and then it will give us the composition relation. So far so good, everybody? Okay, so that is session 3.3. All right, have a nice day. Bye.